Okay, so to understand both dry and moist convection, we actually need to go back and think about the air-sea fluxes that we introduced last week. So last week we just talked about what these fluxes look like at the ocean surface. And you can see that in the graphic here. I've just copied this from our previous lectures. So remember, we had the shortwave radiation, longwave radiation, latent heat, and sensible heat. What we need to think about here is where these different fluxes that are coming out of the surface end up in the atmosphere itself. So where do they actually heat the atmosphere? Because that's going to control where they drive convection. So let's introduce our atmosphere, which is this blue box. And here we're purely going to focus on this convecting region of the atmosphere, so the troposphere, so the lower roughly 10 kilometers of the atmosphere. And this graphic is showing you where these different radiations or heat fluxes end up in the atmosphere. So for the troposphere, it's essentially transparent to shortwave radiation, unless you have clouds and then it's reflective. But in general, it's transparent to the incoming shortwave and it's transparent to the reflected shortwaves. There's no internal heating due to the shortwave radiation. If we think about longwave radiation, the outgoing longwave radiation from the surface is absorbed largely in the troposphere, but then the molecules of air and moisture are re-radiating radiation, and they radiate both down, which is that incoming long wave at the surface, but they also radiate up to the higher atmosphere and then to space. And on average, on net, they actually radiate up and down, so there's more radiation going out, either vertically up or vertically down, than there is coming in from the ground. And as a result of that, the net effect of the long-wave radiation in the troposphere is cooling. And in fact, it's cooling of about 2 Kelvin per day. If you take a parcel of air and track that temperature over a day, it will lose approximately 2 Kelvin. So we call this radiative cooling, and this drives the large-scale sinking of the atmosphere. So if you have air in the troposphere, on average, it's going to sink over time due to this cooling effect. Okay, so we can move on to latent heat flux. So latent heat flux at the surface, remember when you evaporate this moisture, it pulls heat out of the surface ocean, and it's stored in the molecules as this latent heat. We can recover that heat when those molecules stick back together and condense into rain. But that recovery of heat and that dumping of heat into the atmosphere only occurs when the condensation occurs. So essentially this heat source that's going from, or this flux of heat that's coming out of the ocean and going to the atmosphere only actually heats the atmosphere when you get condensation occurring. So somewhere you're going to get condensation and rain falling, and that's where this latent heat flux is felt. So this is really important in moist convection in the atmosphere, but it's an internal source of heat away from the surface. It's not doing anything directly at the surface. Lastly, we have sensible heat flux. And so this one is just the transfer of heat, remember, from the surface ocean to the air directly above due to the turbulence between them. And that directly heats the air above. So if the ocean is warmer than the air, then this provides a direct source of heating for the near surface air, which then makes that hotter and causes it to rise. And so that sensible heat flux can directly drive convection at the surface.